Math often starts as a sequence of operations on a flat page. We learn that squaring a number means we multiply it by itself, a quick calculation to reach a result before moving to the next problem. On a chart, the squares look like this: 1, 4, 9, 16, 25. They seem like isolated milestones, but look at the space between them. Add 3, then 5, then 7, then 9. Every perfect square is separated by the next consecutive odd number. This raises a question. Why does a sequence of jagged odd numbers always result in a perfectly even square? To find the answer, we have to look past the numbers as symbols and see how they occupy space. When arithmetic is translated into geometry, the logic of the pattern becomes visible. Mapped onto a grid, the red square is unit 1. Adding the odd number 3 fills the space around it. Green units wrap the red, making a 2 by 2 square. Adding 5 yellow units expands the structure to a 3 by 3 square. We now have 9 blocks. This specific L-shaped addition is known as a gnomon. By continuing this pattern, every new odd number, 7, 9, 11, acts as a layer that grows the square's perimeter while keeping its shape perfectly symmetrical. In this environment, addition is the process of expanding an object's boundary. However, the shape of the math changes if we move these units into a three-dimensional setting. These pegs are grouped into quantities of 1, 3, 5, and 7. When they are laid flat on a surface, they retain the V shapes that allowed them to nest into a square. Lying horizontally, they still fit together like the layers of our previous grid. But look at what happens if we change their orientation and stack them vertically instead of nesting them flat. These are the exact same quantities, 1, 3, 5, 7, and 9. But in this vertical stack, the resulting structure is a symmetrical triangle. The math hasn't changed. The sum of these odd numbers is still 25. But the vertical arrangement shows that the same numerical sequence can take on a completely different profile depending on how the units are positioned. The final shape of a sequence is determined by the spatial logic of the background grid. This isometric plane uses triangles as its base unit of measurement. If we build our sequence here, we start with one red triangle. Adding a row of 3 blue triangles and 5 orange triangles expands the shape downward, creating a uniform, larger triangle. This base 3 shape contains exactly 9 small triangles. The arithmetic result, 3 squared, remains the same. When we add 7 more purple units to create a base of 4, the total count reaches 16. By shifting the grid from squares to triangles, the same sequence of numbers produces a new physical form, while the underlying math stays perfectly intact. Understanding how these numbers fit together provides a visual shortcut for solving large equations. If we know the square of a very large number, we can find the square of the next number without a long calculation. We only need to add the next consecutive odd number to the outer edge of the shape. This demonstrates that square numbers are the physical accumulation of space. Arithmetic is bound by the way these units must fit together in their environment. When these blocks interlock, they reveal the hidden architecture inside the equations. Mathematical patterns take physical form when viewed from the right angle. To understand these sequences, we cannot look at them as abstract symbols on a page. We must visualize how they build the world around us.